Welcome to the Explainer. So let's just dive right into it because today we are going on a really fascinating trip into the microscopic world of bioengineering. We're going to explore exactly how scientists manage to detect things that are practically undetectable. And spoiler alert, it all comes down to an incredibly elegant mathematical concept known as the IC50. It acts as the ultimate key to unlocking high-precision diagnostics. So get ready, because the science of the incredibly small is absolutely going to blow your mind.
Think about this for a second. How do we actually measure the invisible? It's kind of like trying to find one single, specific drop of water in a vast ocean. And that is exactly the fundamental challenge bioengineers face when they need to detect incredibly tiny amounts of a substance. You know, something like an early marker for a disease, or maybe a trace amount of a dangerous toxin that's hidden inside a really complex biological sample like human blood.
Because you see, to find something practically invisible to the naked eye, we can't just look for it with a standard microscope. If the concentration of our target, which, by the way, we call an analyte, is just vanishingly small, we have to engineer a clever microscopic system. We basically have to force these tiny molecules to reveal themselves to our sensors. This is the exact arena where bioengineers tackle the mind-bending problem of accurately analyzing these microscopic analyte concentrations.
So that brings us to Section 1, the Biosensor Challenge.
To actually win in this arena, scientists have come up with a few ingenious tricks. Honestly, the most clever one is called the competitive immunoassay. The best way to picture this is like a highly regulated, high-stakes, microscopic game of musical chairs. You've got these little Y-shaped structures anchored to the bottom. Those are antibodies, and they are essentially the chairs in our game. And the free-floating shapes above them, well, those are the analytes, desperately fighting for a seat.
Which leads us perfectly into Section 2, the competitive immunoassay.
Now, playing microscopic musical chairs is cool and all, but it's another thing entirely to use that game to measure exact molecular concentrations. To make it work, we introduce a known competitor into the mix. It becomes this tiny molecular tug-of-war. We take a known amount of labeled reference analytes, meaning they literally have a chemical or fluorescent tag on them so our machines can actually see them, and we pit them directly against the unlabeled, unknown sample we're trying to measure from the patient. They are battling it out for the exact same antibody binding spots.
Let's walk through exactly how this dynamic process goes down. Step 1. We add our perfectly measured, known labeled reference into the biosensor. Step 2. In goes the unknown sample. Step 3. We just let them compete for those limited binding sites. And finally, Step 4. We measure the labels that actually manage to bind. The logic here is beautifully simple but so profound. If your unknown sample has a high concentration of unlabeled analyte, they're going to crowd out the competition and steal all the chairs. So, fewer labeled molecules will be able to bind. Therefore, the more of the unknown analyte you have, the lower the signal we measure. It's an entirely inverse relationship.
All right, Section 3, defining the IC50. So this inverse relationship is incredibly powerful. But how do bioengineers calibrate this whole system so it's hypersensitive to even the smallest little changes? Well, it all builds up to the star of the show. Here is the formal definition you really need to know. IC50 is the concentration of the unlabeled analyte that inhibits exactly 50% of the labeled analyte's binding. But, and this is absolutely crucial, don't just view this as some random biological measurement. The IC50 is the ultimate sweet spot of the assay. It's this point of perfect tension where exactly half the chairs are taken by the knowns and half by the unknowns.
And here is why that specific point is basically magic. If you look right in the middle of this falling S-shaped curve, the sigmoid curve, you'll see parameter C. That inflection point right there, that is our IC50. Notice how the math works out. At the extreme edges of this curve, the line is relatively flat, right? But right at the IC50, it absolutely plunges downward. The slope hits its absolute steepest point.
Which brings us to Section 4, maximizing signal sensitivity.
Let's pull back the curtain here and reveal exactly why bioengineers deliberately target this exact mathematical sweet spot. Why does the IC50 inflection point matter so much? Well, engineers actually calculate the reference concentration to intentionally bias the response right into the proximity of the IC50. Because the slope is practically falling off a cliff there, it means that even a microscopic tiny change in the unknown analyte concentration triggers a massive, super obvious drop in our signal. Plus, errors in measurement are completely minimized right here at mid-scale. If you tried to measure at those flat extremities of the curve, one tiny error could throw off your whole reading.
But at the IC50, the signal is so loud and clear that the margin of error just plummets. I actually love this quote from our source material because it totally cements the real-world value of all this complex theory. By targeting the IC50, you are, quote, achieving an amplification for small concentrations of sample analytes. It's just an incredibly elegant physical solution to a really complex data problem. And there's a huge practical bonus to this too. Because this competitive method is inherently so sensitive, it has the massive real-world benefit of saving costs. It completely removes the need for a second labeled antibody, so it keeps our medical tests affordable without sacrificing an ounce of precision. Talk about a win-win.
It honestly is mind-blowing how a tiny biological game of musical chairs, combined with a clever mathematical inflection point, can quite literally save lives. So I'm going to leave you with this final thought. How do these hidden, microscopic sweet spots impact the medical tests that you and your family rely on every single day? The next time a doctor hands you a super precise lab result from just a single drop of blood, you can remember the IC50 working silently behind the scenes. Thanks so much for joining me for this explainer. I really hope this sparked your curiosity about the hidden mechanisms running our world. Keep learning, and I'll catch you next time.